Good morning. So let me start. So I would like to emphasize the most important thing which we discussed yesterday, and that's the causal structure of spacetimes in different theories. And it basically tells you, what is possible and what is not in the spacetime. And this is the classification is based on the real observers, on massive particles, if you want. So whether the massive particle can travel from one space-time event to another or not. And so we distinguish three possibilities. So either we can travel from this point to there, and that means that this point is to the future of that point, or actually it's in the past, or they can never sort of communicate. The observer cannot be in both events at all. And so in Newtonian physics, the surface actually of events which can never communicate together is simply a 3D surface. It's called simultaneity surface, and it's just one 3D surface here. So whatever is above that surface is the future, and whatever is below that surface is the past. So now in special relativity, this structure is replaced with the light cone structure. The light cone is global, so there exists one light cone basically everywhere in the space-time. So for every point in the space-time, the light cone will look exactly the same way. And then again, you can consider three categories. Is the future, which is inside this light cone here, the past, which is inside here, and the events which cannot communicate. And that's the events which are space-like separated, and also the events on the light cone, because they are only related. They can only communicate through light-like particles, through massless particles. So now this structure sort of survives in general relativity as well. However, the light cones are only locally true, and so as you move throughout the space-time, they can sort of twist around, and so locally they look exactly the same way as in special relativity, but globally not. And so you may wonder yesterday whether actually such situation is possible, that I start with one light cone, and so I have to travel this direction here, but then the light cone sort of twists, as it did in the black hole case yesterday, and so then I have to travel this way, but now suddenly it twists even more and more, so that I actually get back to the same point P after some time. And so these things are called. So now this curve actually corresponds to the time curve. We are always traveling in the local light cone. So we are always going to the future of the local light cone. So nothing is wrong with this. However, we form the closed time-like curve. Okay, and so these curves are in principle possible. In fact, they are actually present in very important solutions of general relativity. For example, in the Kerr solution. So we will learn that Kerr solution simply describes a rotating black hole. And so as you go inside a black hole and you go close to the singularity is a very special one, but it basically looks like a ring. But around that ring, actually, you can have these closed time-like curves. Well, people are not that much bothered because everything is hidden behind the horizon, and nobody can really probe these closed time-like curves. And if he can or she, then she cannot communicate this outside of the black hole because she's inside the horizon and it cannot send the information out what's happening. But the closed time-like curves are there. Another nice solution, which is the Taub-Knut solution, which is like Schwarzschild, but not quite. It's more like a gravitational monopole solution. Also has these time-like curves. If you have a rotating string, it also has closed time-like curves. So actually, these things do occur in general relativity and in exact solutions, but they are considered pathological because, of course, I can sort of influence whatever my past was, and I can go sort of like backwards in time, by going forwards in time, and so I can affect whatever I did in the past. So they are considered pathological, and people try to avoid these solutions, or they try to hide the problem. So, for example, as in Kerr, this happens behind the horizon, so people are not bothered by it.
Why you don't bother that it happens behind the horizon? I mean, you can do physics there. You can have a friend and you can talk about physics there.
Okay, we can talk about it later. So Kerr is an exact solution. Kerr is an exact solution, and as such, is very idealized. So now the question is how you form Kerr solution in nature. Typically, the black holes are formed by gravitational collapse. If you form it by gravitational collapse, it's very likely that whatever we see in the exact solution in the interior is not physical. So that has to be replaced by something else. So that's, for example, one answer to this. People have thought about this Taubnat solution for years. So people thrown it away in the 60s, and there's a paper 2 years ago where they say, well, actually, it's not a big problem. We can have these closed time-like curves, but we can actually kill them by something, and. So people still, playing with these things. So now somebody asked yesterday, what type of questions? When do you get your questions for the interview? So this would be an ideal one question for the interview, right? So describe the causal structure of space-time in Newtonian, special relativity, and general relativity theories, and that will be one question, for example. So if you plot something like this, that will be amazing. Questions? So I think this is the most important thing of yesterday's lecture. So now we also discussed relativistic objects. So relativistic particle, and typically people, when they discuss general relativity, they just consider only point-light objects. So let's just a particle. We have a particle, and it sweeps a trajectory in the space-time, and this trajectory is simply described by x mu as a function of one parameter lambda. And the trajectory is typically called world line. Okay, because it's a line. And it describes whatever the particle experiences, so that's why world line. However, you can also consider these more dimensional objects, and so you can consider a string, for example, which is a p equal to 1 brane. So this would be a 0 brane. This guy has 1 dimension, so that's why p equal to 1 brane. And so then the string sweeps a surface in the space-time. So I have a surface like this. Okay, because now it's a surface. It's called world sheet instead of world line. So this is world sheet. And now it's obvious that this is, so whereas the world line is really one-dimensional thing and it's enough to describe it by one parameter, world sheet is a two-dimensional object. And so you need 2 parameters. You basically need x and y directions. So now this is described by x mu, which is a function of 2 parameters, and I'll call them lambda and sigma. Or more generally, these parameters, if you have a p-brane, there may be p parameters, p plus 1 parameters, psi a. Okay, so lambda and sigma. So this a runs from 0 to p minus 1. A. All right. So now what we have also studied, and so is this clear that more dimensional objects can simply sweep more dimensional surfaces in the space-time, and they are called world sheet in case of the string, or world volume if it's more dimensional one. World volume. So now if you have a free particle, so if the particle is free, then you know that the action is simply proportional to an integral over the proper time, which is proportional to an integral over d lambda, and then whatever is here minus eta mu nu dx mu d lambda dx nu d lambda. And so the motion, so this is the action, although it doesn't look like my integral sign. So this is S, still looks like an integral sign. So this is the action, and what you are trying to say here is that you really extremize the proper time. Proper time, something like if you had a space-like trajectory, it would be like a proper length. Okay, so what you are really trying to do is that like extremize length. And so that's a very, very clear geometrical meaning. I'm trying to find such a trajectory. So trajectory of free particle is such so that you extremize the length of the trajectory. You maximize the proper time, or you minimize the proper length for space like GD6. All right. So now, obviously, this has a very natural generalization to objects with more dimensions. So again, the statement will be that the motion of a free string is such that the world shear size, so if you take the area of this thing, will be extremum. Okay, and so that's a general generalization. So now this is described by Nambu-Goto action, and so what it basically is saying is that the d of the volume of world sheet, and that's your action. So it's d of the volume of the world sheet, and so the motion of the free string is such that you extremize this, so that the volume of the world sheet is actually extremum. And so what it is very simple. So we have these parameters which parameterize my world sheet, right? So I have this lambda and sigma, or I call them psi a. And so what you do first is that you sort of write down what the metric on this surface is. Okay, so this metric is induced from the Minkowski metric, and how you simply get it is the prescription. So you have these big indices A, which describe my parameters. So first you write down the induced metric on the world sheet. And that's simply gamma AB, which is induced from the Minkowski metric. So it's given by the Minkowski metric, which we have in our spacetime, eta mu nu. And then you simply write dx mu, d psi A, dx nu, d psi B. Okay, so I take my parametrization of the world sheet of the string. So these are x mu functions of psi. I just differentiate them. I contract the indices mu and nu. So I'm left with indices A and B. What else it has to be than an induced metric? Okay, so this is the induced metric on the world sheet. And this precisely tells you, how big the surface is. The metric tells you how you measure the distances. And so it tells you how big the world volume is. And so you will learn that actually soon that in order to calculate volume, you take the square root of the determinant of this metric. And that's it. So the Nambu-Goto action is simply, and it's interesting that I didn't write it down, but S Nambu-Goto is simply an integral over this p plus 1 psi, and then a square root of the determinant of this metric gamma AB. Okay, and that's it. And if you want, you can put a minus sign, provided that this is really has time-like direction in it, and so the determinant would be negative. And it's negative because of this thing here. All right, so this is the motion of the free string. And now we have to extremize this action, but what it actually means is that I simply extremize world volume. And so these Nambu-Goto actions, so this is also Nambu-Goto action. If you look at this is precisely whatever the prescription is over here. If you take p equals 0, reduces to whatever you get here, right? So in that case, I have only one psi, which I call lambda. So then my gamma has no indices is simply eta mu nu dx over d lambda, dx over d lambda. I take a determinant, but it has no indices. It's one-dimensional matrix, so determinant doesn't do anything. It's still the same thing. And the minus thing, and I recover this guy here, right? So this is the same action, the same principle, but now just a more dimensional version of that. All right. So we have this, and now you understand everything. So let me just leave the strings for the moment. Of course, this is much more complicated than that, right? So if I extremize this thing, so for particle, if I vary this action with respect to my trajectory x mu, I just get that d u mu over d tau equals to 0, or you can write it in terms of the momentum, just multiplying by tau 0, dp mu over d tau equals to 0. Or I can be even more refined and write d over d tau as d over dx, dx over d tau. Okay, so this is my equation of motion for the free particle. But I can also write d over d tau as dx nu over d tau, d over dx nu, just using the chain rule. And so if I plug it over here, I see, so this thing is just u nu. So you can write it as u nu d nu, right? And so I can also write my geodesic equation for the free particle as u nu d nu u mu equals to 0. Okay, and so that's my geodesic motion for a free particle. So now, of course, to get the general relativistic version, you just, as always, you add the connection term. You have seen this in gauge theories, right? So if I want to couple my gauge field to electromagnetism, I just change partial derivatives to partial derivatives plus a mu, the vector potential. I form a covariant derivative, and then I included the coupling to electromagnetism. So similarly, the coupling to gravity will be included by changing the partial derivative to partial derivative plus the connection. And so for general relativity, you just simply replace this partial nu with this covariant derivative nabla nu, and that's the general relativistic version of it. Okay, so that's the future. This is extremely simple here, right? Of course, if I write down the equations of motion for the free string, this is not so simple, right? Because now we have more parameters. Now you have really the determinant of the thing. So the determinant is quite complicated object. You have square root of that. And actually, people still trying to solve. Well, in Minkowski, it's rather simple. But you can study this in any space-time. So I just replace the metric eta mu nu with something more complicated, and then it's very difficult to solve this equation. Okay? So for particle, it's really simple, but for strings, it's not so simple. Right. So now, of course, this has direct generalization. To the case when the particle is not free, particle not free, and in that case, you just simply write down the Newton's law as dp d tau is the force which acts on your particle. And so this is just a 4 force, and a prototype of 4 force would be the Lorentz force, right? So you have particle in electromagnetic field, charged particle in electromagnetic field, and then this would be the Lorentz force, for example. So by the way, these forces can be quite tricky. And so going from the 4 velocity to the 4 momentum, you simply say, well, I just multiply by m0, which is my rest mass. Okay? So now you act on a particle with m0, with some external force. And the statement is, this external force actually can change what you mean by the rest mass. And so there's a short calculation done in the notes where actually I provide you a condition. under which actually the force can change the rest mass of the particle. So now you may be wondering, what about the most favorite one, the Lorentz force law, right? So if you take the Lorentz force, that actually doesn't change the rest mass of the particle. So Lorentz force is very, very special, but the general force will change the rest mass of the particle. It's something like, you can imagine the general force is, for example, so it's radiating away some photons out of your massive particle, and of course the rest mass of the particle changes, for example. Okay, so if you're interested, just look at that calculation there. So one last thing I would like to mention here is that if you look at this action here, so both of them are just Nambu-Goto actions. And so they are really nice in the sense that they have this nice geometrical meaning that they really extremize the wall volume or the length of the curve and whatever. So Nambu-Goto has really nice geometrical meaning. However, it's very complicated and ugly. So Nambu-Goto is quite complicated. And the reason is that you have the square root, right? So you have the square root here, and whenever you have the square root, it's quite ugly, right? So when you're deriving the equations of motion, you have to deal with the square root. Of course, that's just a technicality. But if you are trying to quantize, you don't know how to quantize square roots. Okay, so you know how to quantize free fields or whatever, but you don't know how to quantize square root of something. So this is a problem, especially in quantization. Quantization is difficult. Is difficult because basically all you can quantize is the harmonic oscillator, right? And this doesn't have the form of harmonic oscillator. Another problem is that if you look at this thing here, I said, well, yeah, extremizing the proper time, right? If I wrote everything correctly, I would have m0 standing in front of my integral there. So it would be minus m0 c square and then integral d tau. So now obviously this doesn't have the right limit when you send m0 goes to 0. So this does not work. Does not work in case of the particle for m0 equals to 0. So if you have massless particle, this doesn't work. Yeah. So these are the two main drawbacks of the Nambu-Goto action. And that's why people were thinking, and what you can do is that you can replace this action for this Nambu-Goto action for point particle by something which is called Polyakov action. So instead of Nambu-Goto, we can consider a different type of action, which is called Polyakov action. Well, this is an example where string theory is useful, because actually Polyakov, of course, string theorist. And so the statement is that I can replace this action here with an action which reads like this. So S is now c squared over 2. That's the speed of light. And then 1 over e, eta mu nu, dx mu over d lambda, dx nu over d lambda, and then minus m0 square e d lambda. Okay, so this is the action. The statement is this is the action for point particle as well as that one over there. And this action is much nicer, doesn't have any square root. Right? Moreover, the mass enters only in this term here. So I can easily set m0 goes to 0. Okay, so can set m0 equals to 0, and this will be true for massless particles. Fine, and doesn't have the square root. Okay, so we solve both problems. Of course, there's a price to pay, as always. And if you look at the action, there is this strange thing E. Okay, so there's E here and E there. And so what this E is a new field which you introduce. So E is a function of the parameter lambda. It's like a scalar field, right? So it's a scalar field which I'm adding here. But it's a special scalar field. The scalar field doesn't have any derivatives in the action. So what it really is a Lagrange multiplier. Okay, so we can remove the square root. We can take the limit m0 goes to 0, but at the expense that we introduce the extra. So we introduced extra scalar, not really, E lambda. But it's not like a full scalar field because it doesn't have any derivatives. Okay, so now, of course, what you should do is that you should check that this really gives you the geodesic equations. But the easiest way how to check this is, so now I treat this action as a function of both, of my trajectory x mu, but also of my new field E, right? So then variation, so vary with respect to E, and if you do that, so now you just vary with respect to E, and you get, well, because it's only E, there are no derivatives, you basically get something like eta mu nu dx nu with eta minus m squared, right? And so this has to be equal to 0, and it's an equation for E, right? So because if I vary 1 over E, I get 1 over E squared delta E, and then delta E, so that will be an equation for E. And so from here, you land that this E, and do it yourself, is just given by 1 over m0 minus eta mu nu dx mu d lambda dx nu d lambda. So the equation of motion for E just gives you this. And now I can actually use this solution here, plug it back to the action. And if you do it, so plug back, and then you find that this action actually becomes the Nambu-Goto action. So classically, actions are equivalent. For massive particles. Okay, so if you have massive particle, if I had massless particle, I couldn't do this, right? So this I cannot. But if I have massive particle, m0 is non-trivial, I can write down the solution for E. I can take that solution, plug it back to my action, and you see that the square roots eat each other, and you find back your Nambu-Goto action for the particle. Okay, so this will be your starting point. Again, well, you can generalize this Polyakov action to strings. Okay, let me just write it down. For string, the Polyakov action as Polyakov would be proportional to. So now this is my two-dimensional world shield I have to integrate over. And then we had introduced an extra field E here. So we can introduce another extra field HAB and gamma AB. So gamma AB is my induced metric, which is defined over there. So gamma AB is the induced metric. And this is the internal metric on the world shield. Internal metric. And it's an analog of our E. So it's a higher dimensional generalization of that function. Okay. So again, you see that this action doesn't have any derivatives of HAB. So again, you can think of HAB as a Lagrange multiplier.
So when we had Lagrangian multipliers that came from constraints.
Yeah, and then
The constraint here.
this is the constraint.
Okay.
The constraint. If you want, what the constraint really is that u square is equal to -1. So that's what the constraint really is. Or that u square equals to 0 in the case of massless particles, provided that I switch off then m square. So then I have the constraint to have lambda times something, right? And that something is telling me u square is actually equal to 0. Yes?
Is H, so you call H a metric, so it's actually a metric, but what does it, measure the distance between?
Well, just think, at this point, just think about it like this analog of E. So it's like this Lagrange multiplier. It is a two-dimensional metric. Question is what it really means. So this thing, this gamma AB is really the metric on the worldsheet. It measures how the worldsheet is big. So this thing like an auxiliary metric, if you want, or something like that. I don't really know what the physical meaning of that HAB is, but yeah. And so you see that I don't have that analog term of m0 square E. That means that the string is actually massless. So this is massless string. That's why I have only the first term. So now if you look at this thing here, and if you look at what gamma AB is, well, it's just eta mu nu dx mu over dxi, dx nu over dxi. So x mu's are coordinates in the space-time, right? And as such, they are scalars in the space-time. And so they are functions of this xi, and you have two xi's. So what this really is a massless scalar field theory, where the scalars are the coordinates x mu, and it's a two-dimensional massless scalar field theory. Okay? Only in 2 dimensions, the scalar field is nice theory. It has a special symmetry. It has a conformal symmetry. That's why because you are in 2 dimensions, string theory has all the properties it has. Only in 2 dimensions, the scalar field is nice. Okay, and it's a conformal field theory. So this is basically 2-dimensional conformal field theory. All right, so if you are not bothered by string theory, forget everything what I just said here. But remember that for a particle, I can actually write 2 different actions. One of them has the square root, and that's called Nambu-Goto, and it's perfectly nice. But there are difficulties with setting m goes to 0, and difficulties with quantizing that. And then there is a nicer one, Polyakov one, where you introduce extra field, but then you can take the limit m goes to 0, and then you can. Yes?
Why do you lose the conformal symmetry when you go to 0?
Simply the scalar field is not nice in other dimensions than 2. So you can show that. So it's very simple to show that, right? So the conformal symmetry means I rescale the metric, and the action doesn't change. So this will be only true in 2 dimensions for the scalar field. You'll see that, or it's one-line calculation. In all other dimensions, it's not nice. You don't have that conformal symmetry, and that's why the string theory has to work in 2 dimensions.
So you said that with this new action, it's fine to take the limit m0 goes to 0. Can you explain why that's okay for E to blow up to infinity?
No. So I'm saying this I can do only when m0 is not 0.
Oh, okay.
Yeah. So I'm showing the equivalence of the actions only when you have massive particles, because the first one is defined only for massive particles anyway, right? So I'm saying when you have so if you have massless particles, you have to take first m0 goes to 0 in that action, and then you get a different thing. You just get a constraint that u square is equal to 0.
Yeah.
All right. More questions? Oh, okay. So that's the particles. So now I'm terribly late, but it doesn't matter. So let's do a brief review of this Maxwell theory, which you already hate because we discussed it already for 3 lectures in the classical physics. I'll be very, very brief, and I'll just be using the relativistic notation. So part D is the Maxwell theory. And you already know from the previous courses that's how all this madness started, right? That's how special relativity actually was created and then led to general relativity and so on. So really Maxwell is responsible for all this. So anyway, so you can write down the action which you already studied in your tutorial, so I will not do that. But as in every classical field theory, you have the field equations, which are of course the Maxwell equations, d mu f mu nu equals to minus, this is my stupid units, minus 4 pi j nu as the first set of equations, and then the second set of equations, f mu nu lambda cyclic equal to 0, or completely antisymmetrized equal to 0, doesn't matter. So this is the second set of equations. And then you have the equations of motion, which is the Lorentz force law, and that's dp mu over d tau is E times f mu nu u nu. So this tells me if I have an electron of that charge, then this is the force acting on an electron and it moves according to this. And this tells me if I have some currents as a source, then I have the fields determined by these equations. Okay, so as I did a few remarks, you have seen that already. If you introduce the epsilon tensor, the Levi-Civita pseudo tensor, epsilon mu nu kappa lambda, and because this is also true if I delete the cyclic and mean completely antisymmetrized, all the indices, I can multiply by epsilon, and because this epsilon is constant, I can pull it through. So the second equation is 1, 2, and 3. So the second equation is simply equivalent to also the fact that d mu f mu nu equal to 0, where I define the Hodge f mu nu as 1/2 epsilon mu nu kappa lambda f kappa lambda. So that's the Hodge dual of my Maxwell stress tensor, and you can write down the second equation also in this way. And then it's manifest because the right-hand side is 0, that there are no magnetic monopoles there. So now if I take 1, and that equation, it's obvious that I have 4 equations here. I have 4 equations here, so I have 8 equations, but not all of them can be evolution equations. So for example, if I look at the t component of this equation here, so I plug nu equal to t, I have d mu f mu t equals to minus 4 pi jt. That's the t, so nu equal to t component. And then it's obvious that this is not a true evolution equation. The statement is doesn't have any time derivatives of the field strength f mu nu. Well, it's obvious because this thing I can write as dt ftt plus di fit. Well, this thing f mu nu is antisymmetric, so ftt has to be equal to 0. So this term is not there, and this is just a spatial derivative. So this thing actually doesn't have any time derivatives in it. So the t component of this equation doesn't have any time derivatives, and it's not a true evolution equation. So this is a constraint or initial condition, as we have seen discussing this in the previous course. This is an initial condition rather than an evolution equation. And of course, the same is true here. So again, the t component of this equation will be a constraint. So you have actually only 6 evolution equations and 2 constraints. All right. Questions, comments? So I already also told you that Maxwell equations know about the current conservation and about the charge conservation. So in this 4D language, it's even simpler. So if you look at the equation 1, and you take the partial derivative of that equation with respect to the coordinate x nu, so d nu on 1, so I'll have d nu d mu, d nu d mu, f mu nu is equal to minus 4 pi d nu j nu. But the left-hand side is of the form that this guy is symmetric if you exchange nu and mu, and this guy is antisymmetric, and this is symmetric, so that's 0. So this is equal to 0 identically. So there's no, it's true for any f mu nu. And so we are finding that d nu j nu equals to 0, which is the continuity equation. So the continuity equation is a consequence of Maxwell equations. And this relativistic notation is really simple to derive it. So then I told you in the previous course, okay, let's split this j nu into the rho and j parts. Like rho is the 0 component and j is the current here. And then let's integrate this rho over some spatial volume, and let's call it charge, and let's see that this charge is conserved. So now the similar thing you can do, of course, here, but the picture is slightly different. So instead of, so now you define Q to be an integral over the spatial, so this is a spatial surface. But I can do it covariantly. That means I don't have to split it into rho and j, but I can just say, well, this is a spatial surface. It has a normal and mu. And I can integrate j nu over the sigma nu, where this guy has the normal and nu. So now if the, okay, so what I'm doing is that I'm defining, so this is my spatial surface, sigma, and it has some normal and mu. And provided this normal has components, so if I choose like in the time direction precisely, it will have components 1, 0, 0, 0. And so in that case, what really stands here, so this thing is like d sigma and nu. So this will have only the 0 component, and then there will be only the 0 contribution, and it will be rho times d sigma as we defined it before, right? So now you have this surface here, and the time proceeds this way. So this is time and this is space. And so later on, I choose a different surface. So this is sigma 0, and this is sigma at some later time, sigma t. And then, again, I calculate the charge in the same way on this surface. And the statement is that whatever I calculated here will be equal to whatever calculated there, provided that there is no flux through the boundary. So I have the boundary, so this has, again, the normal and mu. The boundary has another normal and mu, or whatever. But I can have a current going through the boundary. And provided there is no current going through the boundary, then whatever I calculated here equals to whatever I calculated there. So this would be J nu flux through the boundary, through. Okay, and so the calculation is very simple. You know that partial nu j nu equals to 0, so this will be still true if I integrate it. So I have some space-time domain omega here. That's whatever is inside. So now we integrate, so we have 0, integral over omega d nu j nu. Because this is 0, that must be 0 even if I integrate it, right? Now I use the Stokes theorem. and turn it into an integral over the d omega j nu. This is a stupid notation. D omega nu. So now I change the integral from the space-time integral to my integral over the boundary here. But the boundary consists of three terms. It consists of sigma 0, it consists of sigma t, and of this boundary b. It's also b. Okay. But if you see and you remember the Stokes theorem or whatever, you remember that the normal should always point inwards, right? If it points outwards, as I plotted in this way for the sigma t surface, then actually you pick up a minus sign. So this is an integral over sigma 0 j nu d sigma 0 nu, but a minus sign integral over sigma t, because the normal is pointing the other way, the other direction, d sigma t nu, and plus an integral over the boundary j nu d b nu. Okay, so now if there is no flux through the boundary, this is 0. So 0 equals to this minus that plus 0. And you see that the charge integrated over sigma 0 is the charge integrated over sigma t. Okay? So I'm not doing anything new. It's just whatever we have done before, but we have done it before in the 3D language. Now I'm doing in 4D language in the space-time. But it's exactly the same calculation as you are used to it. The only thing is that to define the charge, I don't have to split j nu into rho and j, but I can write it covariantly this way. Question? Comments? Yes?
Can I ask for the relationship of the equation 2?
Yeah.
Is there any relationship between Bianchi identity with that one?
Well, this is sometimes called Bianchi identity, but I don't think so. So I would say that the Bianchi identity is precisely the d mu f mu equals to 0. It's certainly not the Bianchi identity which you would use in the Noether's theorem, as far as I know. But maybe I'm mistaken, so I don't know. So what that second equation is really telling you is that there are no magnetic monopoles, right? So this is copied equivalent to the second equation, and so this is just telling you there are no magnetic monopoles. All right. So now the last thing I want to do is that, again, to introduce these vector potentials. So the equation 2 is automatically satisfied provided I set f mu nu equals to d mu a nu minus d nu a mu. Okay, so provided I do this, just plug it here and write down all the terms, and you find it's equal to 0. So a nu is the 4 potential. So a mu is the 4 potential. And then you find that the remaining equations, so the equation 1 is satisfied, then 1 satisfied. For example, if I set the Lorentz gauge condition, d mu a mu equals to 0, and I have the wave equation. Okay, so then these two equations are equivalent to the equation number 1. And we know how to solve the latter equation. We did it in the previous course. We know that the solution of the wave equation is the solution of the homogeneous equation with 0 right-hand side, so the most general one plus a special one, and the special one is given by the retarded potentials. Okay, so we know how to solve these things. But we can also study the static limit of this. Static limit. And so remember, I can decompose a mu into phi and a. And so in the static limit, I'll say, so a corresponds to moving objects, so it will be phi and 0. So I have to kill a to have the static limit. Okay, that's one gauge. I can kill a. But also the static limit means that dt of phi equals to 0. I'm not changing my phi in time. Okay. So then what does it mean? So if I look at this thing here, so what it is, it's dt of phi, but dt of phi is 0, and di of a, but that's also 0 because a is 0. So this is automatically satisfied. So Lorentz gauge is satisfied automatically. And then what I'm left with, well, okay, so this is box, it has time derivatives. So let's take mu equal to 0, so phi, but box becomes just the Laplace operator. So then I have Laplace acting on phi is minus 4 pi rho, where I set j mu equal to rho and 0 here. Okay, so that's my equation here. But I can also take a static limit here in the Lorentz force. You know that in the non-relativistic notation, it's just dp over, okay, that's right, dp over dt. It's E times E, capital E plus V cross B. But there is no magnetic field. There's just E times E. But you know that E can be written in terms of the phi. So it's minus E gradient phi. So these are the static equations for the Maxwell field. So I have electrostatics here. And this is the electrostatics. Questions, comments? Do anything? So, I went through this very quickly, but it's in the notes and you have seen it already in the previous course, so I hope this is okay. All right, so now we can have a first look at GR. So chapter number 2. And the aim here is really to see how far we can go just using our fingers and not any heavy differential geometry or whatever. So chapter number 2, first look at general relativity. And the aim is to have fun and some historical perspectives and whatever. And so the part A will be conceptual path to the theory. So let's try to reconstruct what actually Einstein was thinking when he was developing general relativity. So as I told you, it took Einstein a couple of months to actually figure out special relativity. And the truth is that if he didn't, well, others would, right? So it was like just a matter of time whether it will be this Friday or next Friday, because people are working on in this field, and they were working special relativity. Oh, they almost got it right. People like Minkowski and Poincaré and Lorentz and all these people, they were very, very close. But the truth is that if Einstein wasn't working on general relativity, maybe we wouldn't have the theory by now. It was really a single work of Einstein, and it took him 10 years. And it's not clear at all if he didn't, what would happen. Okay, so now what he was thinking, right? So motivation number one was, well, if I look at, so he was impressed by the Maxwell theory, right? So he really loved Maxwell theory. And he thought, well, if you start with electrostatics, as written here, this is what the state of art is for gravitation at that time, right? So we had the Newton's law, which was that the force is gmm over r squared. Or if you write it in a fancy language as Laplace did, you can actually write down the Newton's gravity as a field theory. So Newton's gravity at the time was just the Newton's first law. But if you write it in terms of the potential, so gravitational potential, then what you find out is that the Newton's law simply writes as Laplace on phi. Let's call it phi. Okay, Newton, phi Newton. So Laplace on phi Newton equals to 4 pi. And let's just to distinguish that I kill all the units for the Maxwell field, so let's keep the units for gravitational things. So there's Newton's gravitational constant, Newton's gravitational constant, and then rho of matter. So that's the field equation for the Newton's gravitational potential if you cast Newton's theory as a field theory. And of course, what is also known is, if you have the Newton's potential, what is the corresponding equation of motion for the matter? And it's given simply by minus m gradient of phi. Okay, so this is the Newton's theory as it was known in Einstein's times, right? So now if you look at this is precisely the electrostatics, right? So the only thing is that I have a different coupling constant here. So instead of just 4 pi, I have 4 pi g. Instead of the charge density, I have the matter density. Okay, who cares? But then I have a different charge. So this is what tells me, how big is the reaction on the electric field. And so now here m tells me how big is the reaction on the gravitational field. But otherwise the laws are precisely the same. So this looks like electrostatics. And so what Einstein wanted is to create the full Maxwell theory for gravitational interaction. So can we make it to full Maxwell-like theory? Maxwell-like theory. In particular, of course, we have electrostatics or gravitostatics here. So we have instantaneous action at a distance. We have action at a distance. Right? There's nothing which propagates at the speed of light, as in the full Maxwell theory. So we know that in full Maxwell theory, the gravitational waves propagate, or they carry the information with the speed of light. There is no instantaneous action. And of course, there cannot be an instantaneous action because of the special relativity. Right? If you have special relativity, we change the causal structure of the space-time. And so suddenly there is no here and now everywhere, right? Depends on the observer. So now if you say there's an instantaneous action to Alpha Centauri, you don't know at which time, right? And so the instantaneous action doesn't make any sense. Okay, so in particular, get rid of action at distance. So this was his goal, right? So maybe he can create another field theory which lives in flat space-time, which will be similar to Maxwell theory. I just have to create out of the static theory the dynamical one, which gets rid of the action at distance, has some finite speed of propagation, and whatever. Okay. However, there was another motivation, number 2. And that told him, maybe actually this is not the way to go. Maybe I cannot just create another field theory, Maxwell-like field theory in flat space-time. Maybe actually I have to go deeper. And that motivation number 2 was relativity of motion. And so Einstein was really, influenced by that. And so basically, you have to go really, really deep here. What's going on with the space and what's going on with the motion itself and stuff like that. And so basically, historically, there are 2 ways how you can understand the space and how you can understand the motion. So space can be understood as absolute or as a relation. So of course, absolute is what Newton says. So he says, well, space exists on its own. It is there, and no matter whether the objects are there, the space is there, and it still makes sense to talk about this point of the space. Okay, so this was the Newton's perspective. But long before Newton, there was this relational thing, and people thought already in ancient Greece and whatever, they thought, well, it only makes sense to actually talk about relative things. So I can say that I'm standing here because I'm standing here with respect to wherever the floor is, wherever the floor is. Or I'm holding this, that's why we have this relation between me and the sheet of paper, right? So this means that we have adjacency relation between objects. So only the relative things is like I can measure things only one with respect to another. Doesn't make sense to say there is an absolute position for this thing. If there is nothing else, I can compare this with respect to. Okay, and so this was like already Greeks, ancient Greeks, and whatever. So in some sense, introducing the absolute space was, as everything in medieval times, right, a step back, right? So this is the right position. And similarly, you can understand the motion as an absolute motion with respect to the absolute space. So any motion makes sense because it's with respect to this absolute space. Or maybe the motion only makes sense is that like one thing is moving with respect to another thing, right? And so that's the relational point of view of motion. So now, what actually drove Newton to introducing the absolute space is this really, really nice thought experiment. And so well, actually, at that time, you can actually do the experiment as well. It's not only a thought experiment. So Newton introduced absolute space based on the following idea, following experiment. Which is called Newton's bucket. Okay, so what it is, just take a bucket full of water and you start rotating it. Okay, so maybe you can have like a string which you first go around, and then so let's say at time t equal to 0, I have a bucket which is here. The bucket rotates. Bucket is full of water. But because I just started rotating the bucket rotates, but the water doesn't. Okay, so the water here is still. It doesn't rotate at this point because I just released the bucket, so the bucket starts rotating, but the water inside does not. So down the later, of course, there is a friction in the water, and so gradually the water starts rotating as well in later times. And you know that as it starts rotating, it actually forms a concave surface. Okay, so then later on, you have the same bucket here, but now the water forms a concave surface, and both things actually rotate. So the water rotates and the bucket rotates as well. Okay, and this is because of the friction. All right, so now this is, well known from your experience that this is what precisely happens. So now Newton argues, well, if these ancient Greeks are right, there is no absolute space with respect to which I rotate or whatever, and it's only a relational thing. So I have to rotate with respect to something, right? So in the first instance, okay, and so only this relative motion has to have observational effect, right? So now if I look at this thing here, the bucket rotates, but the water doesn't. But no strange things are happening. The water is still, and it has the flat surface. So the rotation of the bucket doesn't matter with respect to the still water. So if you say here, so here the bucket rotates with respect to water. So if the ancient Greeks are right, then there is a relative motion between the water and the bucket, and there should be an observable physical effect. But there is none because the water is still, and it doesn't matter whether the bucket rotates or not. Okay. On the other hand, in this case, both things are rotating. The water rotates and the bucket rotates. There's no relative motion of the water with respect to the bucket, and so there shouldn't be any observable effect. However, we observe this concave surface here. Okay. So this is really so then Newton says, well, that it shows that the relative motion doesn't mean anything, because here there is no relative motion between water and the bucket. Both keep rotating, and so that's why this is wrong. The relative motion doesn't make any effect. It's the absolute motion with respect to what? With respect to the absolute space. In this case, the water is not rotating with respect to the absolute space. That's why I don't see anything. In this case, the water is rotating with respect to the absolute space. That's why I see this concave surface. Okay, so existence of absolute space. Okay. Of course, people hated him, right? So people like Leibniz, of course, they had some some other problems to deal with, like the invention of calculus and stuff like that. But they really, they really hated the notion of the absolute space. But interestingly, they couldn't come up with the resolution. They couldn't come up with, what's wrong with this argument? How can I really defeat this absolute space? And of course, they didn't believe that there is an absolute space, but they couldn't counter example this argument. And it took 300 years for people to actually defeat Newton's argument. Okay, so then actually this problem been revived many times, but no resolution until Mach came. And so he came up with an interesting idea. So maybe it's not the motion with respect to the absolute space, but maybe it's the motion with respect to the matter content in the universe. So motion with respect to the matter content of the universe. So in other words, he was saying, well, in the first instance, the water is not doing anything special. It's just standing still with respect to the distant stars. Okay? And that's why I don't see anything interesting. Whereas here, the water rotates with respect to the distant stars. And that's why I see the concave surface. If there were no distant stars, I wouldn't see any difference. That's what he's saying. This is a very interesting theory. He was a philosopher. He was not a physicist. But actually, people put his thoughts into mathematical language, and Mach principle and stuff like that. They are actually quite interesting theories. And they, for example, explain, if you take this theory, they explain why the inertial mass is the same as the gravitational mass and stuff like that. So this is actually very useful. So now Einstein knew Mach, and he really liked the idea that it must be the relative thing with respect to something, right? But he didn't like the with respect to the distant stars. Because that's like action at a distance, right? It's like really, somehow, the distant stars know that the water rotates here or whatever. So then actually Einstein comes. And he was, friend with Mach and influenced by Mach a lot. But then he says, well, I like the idea of relative things, so it must be relative with respect to something. But at the same time, I don't like this at distance thing. So it must be relative with respect to something local. But it cannot be the bucket as we know it, because that was the Newton's argument. It cannot be bucket, which, because here there is no relative motion of bucket with respect to water. So it must be something else. And Einstein comes with the idea, and so it's the gravitational field. So it's the motion with respect to the gravitational field. The gravitational field, of course, is a local quantity. It's everywhere here is a gravitational field. And it really matters, whether there is a motion with respect to these field lines of the gravitational field or not. So in this case, there is no motion with respect to the gravitational field. In this case, there is a motion with respect to the gravitational field. Okay, and so this is a local thing, local and relative. Okay, okay, but then the question is, if this is true, why gravitational field really matters, right? Why did we choose exactly the gravitational field? And here comes really, really deep thought of Einstein. He says, well, the gravitational field is simply not another field in Minkowski spacetime. It's something more important. It's something which actually tells me what the inertial frame is. Okay, and you know that you measure in Newtonian physics, you measure the acceleration with respect to the inertial frame, right? So now Einstein is saying you should be measuring the acceleration with respect to the gravitational field. So, and then he concludes that the acceleration, if it were to be measured with respect to the gravitational field, there is no really big difference between acceleration and gravitation. So he's saying acceleration is something like a gravitational field, because both of them basically tell me what the inertial frame is, right? So I measure the acceleration with respect to the inertial frame, not with respect to the absolute spacetime. But it really, the acceleration and gravitational field are basically the same things. And this was the crucial idea of Einstein. So that's when he understood that he cannot simply just write another field theory in flat spacetime, right? Following Maxwell's ideas. But that he has to actually recreate everything. He has to actually start thinking about, what it means an inertial frame, and that the gravitational field plays a special role in all of physics. It tells you what the inertial frame is actually. Are there any questions? There's an historical thing. Okay, so now let's be more concrete and let's really put this into simple mathematics. So, how you convince yourself that acceleration is basically like a gravitational field is through a principle which is called principle of equivalence, which was known but not appreciated. Okay, so part B is the principle of equivalence. So now let me start with the version everybody knows. So now if you write down the force law, the Newton's force law, you write that the force is given by ma, which is the mass times acceleration. But if I am in gravitational field, in a uniform one, I also write mg. Okay, this is the force which you know from your high school. However, look at this m and that m, they play completely different roles. So the m here, it tells me, how the object reacts on the gravitational field. So this is a gravitational mass, mg. So how the object reacts on the presence of gravitational field. Whereas this m tells me, well, if I apply the force, how much my object starts accelerating. And that's called inertial mass. So this is mi, which is the inertial mass, inertial, and this is the gravitational mass. Okay, but everybody knows that they are the same, right? So what people say, well, mi is equal to mg. For some reason, nobody understands, apart from Mach, actually. So if you put Mach's theory into mathematics, he can predict that mi equals to mg, provided that there is sufficient mass in the distant stars. If there is no sufficient mass, they are not equal. But if there is sufficient mass, that they are the same. So anyway, so this we know from experiment and experience. So, okay, there are different things, right? So in experience, we know this is true. But people still designing experiments actually measuring this. And they can measure this like really to high precision. Namely that actually mi over mg is a constant. And they can measure that. So if this is true, then of course, a equals to g. And I know that the acceleration is the thing, is equal to gravitational constant. It means that all bodies fall with the same acceleration gravitational field. The same acceleration. All right, so this is one version of the equivalence principle. And you see that you already knew it. That I'm just saying all bodies in the gravitational field fall with the same acceleration. This is not true for the electromagnetic force, right? If I did write here, instead mgg, I would write E times E, right? Then of course this E is not the same as mi. And so different bodies will have different E, different charge, and they will fall differently, right? So this is not true for the electric force, but it's true for the gravitational force. So gravitational force is special, right? It has something to do with acceleration. So now the most ingenious idea, as Einstein puts it, which led him to discover general relativity, is this idea of Einstein elevator. Einstein's elevator. So what Einstein says is that if you are an observer who is confined to an elevator and you don't have a window, you cannot distinguish the situation when the elevator is sitting on the surface of the earth and there's a gravitational pull down, g, or the elevator is floating into space and there is an acceleration upwards, this acceleration g. So he's saying these two situations are the same. The guy in the elevator doesn't have a window, and I have the acceleration upwards, which is equal to g. And he's saying this is the same thing as if you have this thing placed on the surface of the Earth, where there's a gravitational acceleration g. And the statement is the guy cannot distinguish these two cases, provided he doesn't have a window. Okay. So in other words, we can mimic gravitational field by going to the accelerated frame. Okay, so that was the idea he had. And as we shall see, you basically derive all predictions of general relativity from this idea. So by the way, now people claim that physics is not about these philosophical ideas, that it's not playing with the elevators and stuff like that. If you ask Pedro, he will tell you we should be doing hard calculations and not thinking about elevators. But actually, I think it's very, very important to think about elevators. All right, so let's look what this simple idea gives us, and one prediction which immediately comes out of this, and Einstein basically had it immediately after he realized that gravitational force is special and can be mimicked by acceleration, is that photons get redshifted in the gravitational field if they climb up the gravitational potential. And let me present this very simple derivation which Einstein did. So gravitational redshift it's an immediate prediction. And so let's see, I have a long elevator here, which is on the surface of the Earth. And then I shine light upwards. And it starts climbing up. So this is in the gravitational field G. And let's say the elevator is of the length delta H. And the statement is that if I shine it here with frequency omega, actually upwards, because the light has to climb up the gravitational potential, it will have different frequency omega prime up there. Okay, so now how to calculate this is that we, according to Einstein's idea, we know that we can mimic this gravitational force by acceleration. So in other words, this must be equivalent to the fact that I have the elevator, which is accelerating upwards with the gravitational acceleration here. So now I shine the light. But, so this light again has to, so this is delta H of the elevator. But the light travels actually at a finite speed, c, right? And so as it climbs up, the elevator actually moves a little bit upwards, right? So the elevator is now over here at the time when the light actually reaches the top. Okay, and moreover, this elevator, if I start from the zero velocity, will have at that point velocity which is equal to g times time it takes for the light to travel upwards. Okay, so now what is this time? So this time is simply c times t equals to delta h plus 1/2 gt squared. So this is how much I have to travel with my light. It's the original distance delta h plus 1/2 gt squared, how much I rise up. But of course, this is small. So if time is small, this is small. So this is approximately delta h. So we can make this approximation here. And so all we really need is that t is delta h over c. So then the velocity of the elevator when I observe the light up there is v is gt, and t is delta h over c. So it's g delta h over c. That's my velocity of the elevator up there when I see the light. All right. So now comes your tutorial. So of course, what's happening here is that the observer, as he sees the light up here, is moving in that direction. So he's moving in the direction the light is moving, right? He has some non-trivial velocity v. So what it means is that he experiences a Doppler shift, right? So if I'm moving away from the light, I see the light with a different frequency, right? And so we can calculate what this frequency is. And so you will do it in your tutorial. So anyway, so at the bottom, my wave vector of the light is just omega over c, and then I'm shooting the light upwards. So this is my z direction. So this is z, upwards, and this is just the wave vector at the bottom. But up, I have k prime mu. And if you want, these two vectors are connected by the Lorentz transformation, right? So I'm just transforming to a frame which is moving with velocity v in that direction. So they are related by and they give you the Doppler shift. So now it's omega prime over c 1, 0, 1. And you will derive in your tutorial that this Lorentz transformation or the Doppler shift is given by omega over c, 1 minus beta, and then 1, 0, 0, 1. So this is what stands in front of this thing here. So it's just a special relativistic Doppler effect. Of course, now I am considered, so beta is just v over c, gamma would be the Lorentz factor. Typically for small velocities, gamma is 1, and you have to consider only the term. So then you know that the omega prime, so this is equal to, of course, omega prime over c, omega prime over c. So omega prime is gamma omega 1 minus beta, which is like omega 1 minus beta due to the Doppler shift. Okay, so this is omega 1 minus, and beta is v over c. So v is here. So v over c is g delta h c squared. 1 minus g delta h over c squared. So this is the Doppler effect, if you want. Doppler. And so our prediction of the theory is that the gravitational redshift, which is omega prime minus omega divided by omega, and if you combine these two results together, it's just minus g delta h over c squared. So you find that if you shine the light up here, then the light will get redshifted by minus g delta h over c squared. So this is an amazing prediction of just playing with the elevators, right? And this was one of the experimental tests of general relativity. So Pound and Repka played with this in 1960. they get a Nobel Prize for this? Probably they did. So basically what they did is they had a flashlight and they shined the light up the tower, and one measured the frequency down and one measured the frequency up. And of course, it takes some precision, but anyway, and they got a Nobel Prize for this. Okay, so just for this elevator idea. Okay, so one last thing I want to mention here is that if the frequency changes where you are in gravitational field, if I have one frequency here, another frequency there, of course, frequency is something which drives your clock. It measures your time. So the proper time of the observer at that point, you would call is 1 over frequency. Okay, so the proper time of an observer at that point is proportional 1 over frequency. And so what it means is that basically that the proper time goes differently here, and it goes differently there. Actually, it goes more slowly here than there. So in strong gravitational field, proper time goes more slowly. So I have another advice for you. So due to special relativity, you know that you have to be moving fast so that you actually live longer. And now you know that actually you should be close to strong gravitational fields so that your time goes more slowly and you live longer. So the best is like during the day to move really, really fast, and at night to sleep, close to heavy books or something like that, so that gravitational field around is very, very strong. So anyway, so the first prediction is that there is this gravitational redshift, and that the time goes differently depending on where you are. Questions?
Just wondering why the bottom and the up frames are inertial frames, so that we can apply special the burst to.
So here, yeah, but at that instant I'm sort of inertial, right? Well, you are right. It's not completely inertial, but yeah.
You can just create an observer to create the expression k times velocity of the observer, right?
Okay.
The Lorentz scalar.
Yeah.
It gives you the frequency as seen by the observer. Then you change reference frames and calculate it in this frame. But then you get this expression. But since you build a scalar, it doesn't matter in which frame you calculate.
Well, but that's true. Well, it's true everywhere. Yeah. Yeah. Thanks. All right. Well, thank you so much. Tomorrow we will see more consequences of this Einstein elevators idea.